So the last section we're going to go through in this introduction to the nervous system is talking about how the nervous system communicates from one cell to another cell. So when we're thinking about synaptic transmission in the CNS, there are two things to consider. One is the presynaptic neuron, so that's the one before the synapse, and that's where one neuron will talk to another neuron. That's called your synapse or your synaptic cleft. And so you have your presynaptic neuron. So this is the neuron that is sending a message. So for example, a sensory neuron talking to an interneuron, talking to a motor neuron. Okay? And so we have our presynaptic neuron and our postsynaptic neuron, and that's the one receiving the message. And the synapse is the one in between. And they talk by releasing a neurotransmitter. So a neurotransmitter is released, which binds to the dendrites in the postsynaptic neuron, receptors in the dendrites, and then we go on through the whole process. But what we have is we have excitatory synapses. So in other words, we have signals coming in and we have a neurotransmitter that's released that triggers this one and excites this next postsynaptic neuron. So in other words, the electrical activity in the presynaptic neuron increases excitability of the postsynaptic neuron. So it's basically a go. And we have inhibitory synapses that do the opposite. They decrease the activity in the postsynaptic neuron. And of course, as I mentioned before, we have lots of transmissions going on. So if we look at our presynaptic neuron, so here are our presynaptic inputs talking to this cell. And you can see this is called convergence of input. You can see that this one postsynaptic neuron is being influenced by lots and lots, potentially thousands of other neurons. And then we also have divergence of output. So one cell, so this postsynaptic neuron becoming the presynaptic inputs on the next cells, on talking to the next ones, is influencing lots of other cells. And it can potentially talk to thousands of other cells and therefore influence thousands of other cells. But how do these cells influence each other? So if we look back at our neurons, this is our little neuron, the end of our neuron, okay? And this is the one that is in our presynaptic neuron, is going to talk to our postsynaptic neuron. So they're going to talk. And so basically, remember, an action potential comes down the axon and then reaches the axon terminal. And at this point, it causes the release of neurotransmitter into the synaptic cleft, which then binds to receptors on the postsynaptic neuron, triggering often sodium channels to open, for example. And so really, the amount of neurotransmitter that is released from that presynaptic neuron depends on the number of action potentials arriving at the axon terminal. In other words, how intense was that signal? Did you hit yourself gently or did you hit yourself hard? If you hit yourself hard, you have lots of action potentials coming down, therefore lots of neurotransmitter release. If you hit yourself gently, you just get a couple of action potentials and a little bit of neurotransmitter being released. And so the neurotransmitter is released, binds to a receptor on the postsynaptic neuron, and this generates a graded potential that varies in strength with the amount of neurotransmitter that is released and the time that that neurotransmitter stays in that area, stimulating the receptors. So basically, the presynaptic neuron releases neurotransmitter, causes a graded potential in the postsynaptic cell. And if you're looking about the synaptic delay, so the amount of time it takes for this whole process to occur in the synapse, it's about 0.5 milliseconds, okay? And you get removal of this neurotransmitter. It can be reuptaken. It can be broken down by enzymes. It can be taken up by other types of cells, for example. So what's actually happening with neurotransmitters? So our action potential has been come down. So pain again, okay? We've generated lots of action potentials. The action potential arrives at the axon terminal. This triggers its voltage. Remember, that's what an action potential is. It causes these voltage-gated calcium channels to open. Calcium enters into the cell. That calcium entering into the cell triggers through a whole variety of processes the neurotransmitter, which is stored in these little vesicles, these membrane vesicles, to be released into the synaptic cleft. The neurotransmitter now binds to receptors on the postsynaptic neuron, whatever that might be. It might be another neuron, it might be a muscle, it might be a gland. And either, depending on what the neurotransmitter is, it either causes an excitatory event, if it's a stimulating receptor and a stimulating neurotransmitter, or an inhibitory event, if it's an inhibitory neurotransmitter, for example. And it causes this excitatory or inhibitory event, and that is your graded potential on this next cell. Okay, and then if that signal is strong enough, we get an action potential in the next cell, presuming it's a neuron. But it might not be. It might be a muscle or a gland. And then, like I said, the neurotransmitter effects are terminated by reuptake. They can get taken back up, degradation, or diffusion away. So like I said, these postsynaptic potentials, they can be excitatory. So in other words, that can lead to a depolarization. So here we have our resting level. The signal comes in, neurotransmitter is released, and we get a graded potential. It is called an EPSP. Okay, it's excitatory postsynaptic potential. And it means we're coming closer to threshold. It can also be inhibitory, so it might be an inhibitory neurotransmitter, and we get an IPSP, inhibitory postsynaptic potential. And we move further away from threshold, meaning we're less likely to get an action potential because we move further away from that threshold point. And EPSPs and IPSPs are both types of graded potential. A single EPSP, as you can see from this, can't induce an action potential. But EPSPs can summate, and IPSPs, of course, to influence that postsynaptic neuron. So they can add up, you can get EPSP more and more signal until you reach threshold, and then you get an all or nothing action potential. But of course, they can talk with each other. So EPSPs are cancelled out by IPSPs, inhibitory postsynaptic potentials. And so most neurons receive both excitatory and inhibitory inputs from thousands of other neurons. So if you're looking at this postsynaptic cell, you can see it's receiving excitatory information from these neurons, excitatory from this one, but inhibitory from this one. So all of those things add up. And only if the EPSPs predominate and bring to threshold do action potentials actually occur. So therefore, when we're thinking about this synaptic integration and whether we have excitatory or inhibitory signals, it's all about whether the neurotransmitter and the receptor, whether they are actually the correct type to dictate whether we will be stimulated or inhibited, or whether that neuron will be stimulated or inhibited. So remember, here is our presynaptic neuron again. Release of stimulus comes in, action potential along the axon, simulates the release of a neurotransmitter. And acetylcholine is one neurotransmitter that is mainly, not always, but mainly stimulatory because it combines to different receptors. And when it's stimulatory, it triggers the release. The neurotransmitter binds, opens a ligand-gated channel, and triggers sodium to come into the cell. And as sodium comes into the cell, of course, the inside of the cell becomes more positive. So it's excitatory because more sodium is coming in. And as that sodium is coming in, we generate an EPSP. There's our trigger, and oops, nice little EPSP. The cell has become positive. Our postsynaptic neuron has become more positive. But at the same time, it might be inhibitory. Okay, so you have inhibitory neurons. And so in this case, an inhibitory neurotransmitter, an example is GABA. And so this binds to a receptor, the GABA is released, so stimulus comes in, presynaptic neuron, action potential all the way along, releases a neurotransmitter, which in this case is GABA, binds to an appropriate receptor, so the GABA receptor, and this triggers potassium to leave the cell. And if potassium leaves the cell, it becomes less positive or more negative, and therefore we get an IPSP. So that is an inhibitory postsynaptic potential. So it's an inhibitory signal. So in other words, the two signals, the EPSPs and the IPSPs, are talking with each other and talking to try and either stimulate or inhibit another cell, whether that's a neuron or a gland or a muscle. And I talked a little bit about summation earlier, and this temporal summation is when one or more presynaptic neurons transmit impulses in rapid fire. In other words, we're getting lots of signal coming in from a single one or more presynaptic neuron. And this is where you'll get summation of your EPSPs to bring to threshold. You then have your spatial summation, and this is where your postsynaptic neuron, so this one is stimulated simultaneously by a large number of terminals at the same time, which again are stimulatory in this case. So signal coming in from one neuron and from a different presynaptic neuron. So leading to this, the stimulation and spatial summation, space from a different space. And then we need to bring all of this information together. So if we look at this postsynaptic cell, you can see it's being stimulated by this neuron, stimulated by this neuron, and inhibited by this neuron. And they all add up. So we get summation of postsynaptic potentials. So you can get summation. So if they don't come quickly enough, you get EPSP, EPSP. It's quite slow. So you don't get an action potential. You get temporal summation, EPSP, EPSP, leading to temporal summation. You might get spatial summation coming in from different places, from one place and then another place, and then they add up together. So this one and this one have made their way to the axon hillock and have generated an action potential because they've come in spatially from different spaces, but at the same time. And then you get cancellation. EPSP plus IPSP means nothing. Okay, so it's all about summation of postsynaptic potentials. So final little question for you. Read the question and press pause when necessary. Press pause and then give us the answers. Okay. Regarding postsynaptic potentials, EPSPs cause hyperpolarization. That is incorrect. EPSPs cause depolarization and a small increase in positivity within the cell. Sodium has come into the cell. A single EPSP can induce an action potential. That's false. You need multiple EPSPs to generate an action potential. Glutamate is an example of an excitatory neurotransmitter, whilst GABA is inhibitory. That is true. Glutamate is generally stimulatory or excitatory, and GABA is generally inhibitory. Most neurons receive both EPSPs and IPSPs. That is correct. Most of them are being stimulated and inhibited, and it's all about summation, which one predominates. Spatial summation occurs when one or more presynaptic neurons transmit impulses in rapid fire. That's incorrect. That is temporal summation. Spatial summation is when the postsynaptic neuron is stimulated simultaneously by a large number of terminals at the same time.